We are starting with our course on 8051 microcontroller. That is the first microcontroller we are going to deal with in this course. Myself, Dr. Vishali Rao, and I have experience of teaching microcontroller and embedded for last 10 to 12 years. Going further, um I don't know out of you how many of you were there during the demo session we have taken on 8051, but then also in short, we'll go through all the points of 8051 microcontroller. So this 8051 is the 8-bit microcontroller. And while going to the microcontroller, at first we have to understand the difference between microcontroller and microprocessor. So that in short, we'll try to look here. So if you can see the diagram which I am trying to show here, the CPU, and then with help of the bus, data bus and address bus, the remaining peripherals are connected to it. And what are those peripherals? Random access memory, read-only memory, I/O port, timer counter, and serial I/O. They are external connected, or externally they are connected to your CPU. That is how the processor is there, which is generally there in the computer, our computer, or in the laptop. The system is generally like this. And the reason is we have to deal with many different things. At one time, we have to go for Excel, whereas for other time, we have to go for image processing. And at the third time, we have to do some programming, some Python on it. So for the variety of things, we are going to use our CPU, and that's why to make it general purpose, to make it accommodating many things. In this way, the uh, memories and IOs, they are externally connected so that we can deal with many things. And microprocessor itself is the general purpose. It can deal with many things. It is not restricted to some bit. It can go for 32 bit. It can go for 64 bits. Not single core. It can go for multiple core. So the emphasis is on the computing which the microprocessor is doing. It can go for large computing there. Whereas in case of microcontroller, here we are targeting the microcontroller so that it will work for specific applications. That way it is there. So as we are using it in the separate systems or the embedded systems separately for some particular application, we don't need it to be very much general purpose. And that's why if you check for this diagram, so this diagram have CPU, read random access memory, read-only memory, I/O port, timer, serial communication port, all on single chip. That is how the microcontroller is there. That is the basic difference between microprocessor and microcontroller. Okay, so taking this idea in mind, we will go further. Now, even before moving with this microcontroller, we must know two different architectures on which the microcontroller works. And those architectures are, first one is von Neumann architecture. And look what this architecture is trying to tell. The CPU means the central processing unit, where the processing is happening. It is dealing with program and data memory, and this program and data memory, it is in one stack, and the single bus is dealing with it. Let it be, it is the 8-bit bus. As we are talking about 8051, we are talking about 8-bit bus. So when you are fetching the address, you can't fetch the data at the same time. Okay, one by one you have to deal with. That is what happening here. Okay, so limited bandwidth we can say is happening here, and that type of architecture is called as von Neumann architecture. And the second type of architecture where CPU for its processing, this central processing unit for processing, is taking the program from the program memory, which is a separate stack, and taking the data again from the separate memory, which is again the separate stack. And what that architecture is called as Harvard architecture. Again, it depends on application. what is our requirement, and that way the architecture can be selected. So this is Howard architecture. So what two architectures we have to talk about? One is von Neumann and other one is Howard architecture. And simply try to understand that obviously in the Harvard architecture, operating bandwidth will be more compared to von Neumann. What is more? Operating bandwidth will be more. So two things we are keeping in mind. One is limited operating bandwidth in von Neumann architecture, whereas improved operating bandwidth in Harvard architecture. Then one more important thing is this von Neumann architecture is generally called as complex instruction set architecture. What? CISC architecture. Whereas this Harvard architecture is called as what? RISC architecture. That is reduced instruction set architecture. So that way, CISC architecture is the von Neumann architecture with limited bandwidth. RISC architecture is Harvard architecture with improved bandwidth. At present, just trying to understand this thing, not going in much detail. Whenever we are entering to the microcontroller, we'll look in detail with it. Expecting you got this thing? And I'll go further. Okay. Going to the next slide. Here in short, I'm putting comparison of 8051 family in front of you. And in that family, there is 8051, 8052, and 8031. These three microcontrollers are there. And they are compared on basis of what? Read-only memory, random access memory, how many timers are there, how many IO pins are there, how many serial ports are there, and how many interrupt sources are there in the microcontroller. Try to understand. As we are comparing them on this basis, obviously you can read these values 4K, 8K, and so on. That is very simple for you. But try to understand that whenever we have to go for selection of microcontroller, what we have to look inside it, we have to look for these features. We have to look how much is the ROM. At first, to put our requirement of ROM, and then to look in the microcontroller, how much is the ROM. Similarly, RAM, how many timers are there, how many IO pins are there. Obviously, it depends on our requirement. In what application we are going to use that microcontroller, and how many pins or IO pins are required there, and how many are there in the microcontroller. Is it right? So these features, they are very important while designing some application. We have to look inside it. It is not required. Optimum requirement has to be satisfied. Is it right? We don't have to go for very hi-fi microcontroller for a simple application or very simple microcontroller for a hi-fi application, right? It must match. So look, ROM. How much is ROM in case of 8051? It is 4K. Okay, 4 kilobyte. It is in byte. Ours is 8-bit microcontroller, and everything we will talk in terms of what? Bytes. So 4 kilobyte is the value of ROM, whereas in 8052 it is increased, and how much it is? 8 kilobyte. And what they are trying to say here, it is 0 kilobyte in 8031. So how to get the ROM? So whenever the ROM is required, it has to be externally connected. What we are getting from here? Internally, in these two cases, ROM is there, but in the second case, external ROM has to be connected. Similarly, RAM. How much is the RAM? 128 byte of the RAM is there in 8051. Try to understand when I am saying 128 byte. So it is a stack of how much? 0 to 127. And each stack is width of how much? 8-bit. That way, the RAM, that stack of random access memory. You can access it randomly. You can store your data. You can recall that data. Again, it's addition. You can store there. So like a scratchpad, you can use this part, that is RAM. And it is in what? Bytes. Further, in 8052, it has been increased. How much it is? 256 byte of RAM is there. And again, in 8031, 128 byte of RAM is there. Now, look to the timers. Timers, two timers are there. In 8051, timers are the internal circuitry which is setting the time according to the requirement of our program. Similarly, 8052, which is the next version of 8051. Is it right? 51. Next one is obviously 52. So it has improvement. What improvement? 3 timers. In all these cases, improvement is there, as well as in timer, the improvement is there. So how many? 3 timers are there. Whereas in 8031, how many? 2 timers are there. Okay, we'll talk about the IO pin, and 32 IO pins are there in all the cases, and try to understand 32 IO pins means in terms of 8 4s are 32. How many ports? 4 ports are there. Okay, together we are using bunch of 8 pins. That's why I am saying 8 4s are 32, and thus 4 ports are there in each microcontroller. Okay. Then other than these, there is a serial port, single serial port for the serial communication. It is there. We will explore the serial communication further. Similarly, interrupt sources are there. Interrupt sources means which can stop the program which is running inside in between. Okay, due to some important procedure to be done, interrupt sources can interrupt the program. So they can be the maskable or non-maskable interrupt. Non-maskable means whatever is the program running, we can stop it. That is non-maskable interrupt. And maskable means we can ask them to wait. Though the interrupt is coming, we can ask them to wait. So how many interrupts are there? 6 in 8051. 8 in 8052 and 6 in 8031. Now here, what we have to understand, we got the feature, we got the comparison. Obviously, we are interested in 8051, but we have to see that how for some, keeping some system in mind, what different thing they have added here to make a microcontroller. This was the first basic microcontroller which was designed. And later on, many things got added to it. Is it right? So I'll go to the next PPT. Is this clear to you? Just for 1 minute, I'll keep it here. Is it okay to you?
Yes, ma'am.
Maybe. Okay. I'll go to the next one. Here I'll not put much time. These are even more member of 8051. One more thing I want to clear that 8051, it has been made by Intel, Atmel, and many of the companies by different name. Now they are calling it as 8951, 89C51 or 8951. It is by whom? By Atmel. That way, different by different companies, it has been made, but basic structure was whatever I tried to show you in those features. And this Atmel, for the higher version, it added what? Watchdog timer, analog comparator, and in-system programmable. Okay, so these are few features, few additional features which got added. Even the name, they are trying to explain what they can do. What is it? Watchdog timer. It can keep the watch on some process. Analog comparator. Everything is happening digital when we are talking for microcontroller, but somewhere if analog comparison is required, we are dealing with analog input. That time we need the analog comparison. So that is also present there. And in system programmable, when the microcontroller is in the system and there you want to change the programming, that is in system programmable. Okay, we don't have to go in much detail. I'll come out of it. And here is the block diagram of 8051. We have to understand it and then we'll move to the architecture of 8051. Okay. Expecting this flow is going okay. In case you have any problem or any query, please tell me. Okay. So talking about the block diagram of 8051. Might be the students, those who are in this meeting, they are from variety of classes. That's why I'm trying to tell from the basic. So microcontroller, it is for doing some mathematical operation, and to the output, those operations are available. So for doing the mathematical manipulation, there is the central processing unit. As the name suggests, what it is doing? At the bit level, some operation it can perform. It is the central processing unit. So everything is coming to center and here those operations are happening. Which operations? Logical and arithmetic operation. By the name, you got it. What two operations? One is arithmetic operations and other one is logical operation. Under this name, you can accommodate different operations. In the logical operations, ANDing, ORing, XORing, and so on, different operations are there. Whereas in the arithmetic operation, addition, subtraction, multiplication, divisions are the operation which can be performed. So CPU is able to do it. In CPU, there is ALU, arithmetic logic unit. What important part is there? Arithmetic logic unit. It is doing these operations in arithmetic logic units. Okay. And at what level? At the bit level. So what you have to understand, we are dealing with bits. Okay. So whatever is our data, whatever are the values, we are converting them to binary. We are converting them to the binary. One more important thing is at the level of machine language, which is understood by 8051, hexadecimal system is used. So it will be homework for you people to understand or to learn what hexadecimal system so that you will get the idea. Okay. So at many places, what will come in picture is hexadecimal numbers, and in hexadecimal, we have to talk. In general, talking about hexadecimal, what we know is like in hexadecimal, we are using the representation from 0 to F. Is it right? And this 0 will be represented by how many bits? 4 bit. And what those 4 bits are there for representing 0? It will be 0, 0, 0, 0, 4 bits. Okay. And how the F will be represented? Again by 4 bit. And those will be 1, 1, 1, 1. Clear? We are moving from 0 to F. That is 0, 1, 2, 3, so on up to 9. After 9, what will be there? A, B, C, D, E, and F. These many 15, 0 to 15 means in total 16 values will be there. And how in terms of binary they are represented? By 4 bit, it will be representing from 0, 0, 0, 0 up to 1, 1, 1, 1. Ours is 8-bit microcontroller. Okay. So as it is 8-bit microcontroller, we can deal with how many, how we can deal with? We can deal in hex, it will be from 0, 0 up to FF, we can deal with on the port. Is it right? From 0, 0 means 4 and 4, 8 zeros, and going up to F and F means 4 and 4, 1. That we can deal with. Okay. So CPU is dealing with the binary values. Then CPU is supported by the oscillator. Whatever changes are happening in CPU, whatever operations are happening in CPU, they have to be synchronized with oscillator. Okay. This oscillator, it is generating a particular value of frequency with help of crystal oscillator and this capacitor. Okay. And in synchronization with this, our CPU will run. This is the clock frequency. What this is called as clock frequency. Whereas CPU works at machine frequency. Okay. And machine frequency will be lesser than the clock frequency. We'll deal with it. So clock frequency is getting divided, acting as a machine frequency. And with that machine frequency, our CPU is doing the operation of arithmetic and logical operations. Okay. On the other side, CPU is directly interfaced with interrupt control. Okay. External interrupt INT0 and INT1, these two pins, directly they can stop the operation of CPU. Okay. Depending on the importance of the interrupt. So interrupts are there and these are flag bits. TF0, TF1 and T1 R1. Okay, so these two are what? Again, the flag bit which again can stop the working of CPU if program is demanding in that way. Okay, just 1 minute. I'll go back in interrupt case. 6 interrupts they are saying. Okay, so that way interrupt control is there. So you got it. CPU is doing the operations by what you can say arithmetic logic operations supported by the oscillator, and interrupts are there directly in conjunction with CPU. Now further, this is the bus. Okay, and it is connecting what? Our ROM, 4 kilobyte of ROM to the CPU, 128 byte of RAM to the CPU. Look, how is the ROM? ROM is one directional. We can just fetch the program, decode it, and ask the CPU to work accordingly. Are you getting? It is not both directional because it is read only memory. We can read from it. Once the program by the programmer is burnt in it, we can just take whatever instructions are there one by one so that CPU will act accordingly. Okay, so this is the ROM, which is one directional. One by one we will be taking the instruction, the decoded instruction. Accordingly our CPU will work. If those instructions are suggesting fetching the data from RAM, that we are doing. If those instructions are suggesting saving that data in RAM, again that we are doing. And that's why how is the RAM interface? Both way. IO type, sorry, not IO type. You will confuse IO with the input outputs. So it is what? Give and take relation is there with the RAM. It is random access memory. We can save in the memory, we can take from the memory. That's why it is both directional. Okay, so ROM is for program, one way. RAM, it is for data, both way. We can take the data as well as after completing that particular process in some memory location, we can save that data also. So this is one part. After that, there are timers. How many timers? Timer 0 and timer 1. This we can use for setting the internal time for some operation. Okay. Again, my program can utilize that timer. In the program, I can set the timer, particular value of the timer, and after that much time, I can ask to do some operation. So that way, timer 0 and timer 1, two are available in 8051. Okay. They have external access also by the pin T0 and T1. Now, after that, there is bus control. Okay. So this bus, controlling the bus, here is the logic, which is what you can say a control place for controlling the bus. It is going to what? IO ports. How many IO ports we have? 4 IO ports. And each IO port of how many bits? 8 bit. Or how many pins? 8 pins. 8 4s are 32. So 32 pins are available here. Before the pin, latches are there so that you can latch the value on them. You can keep the value for some time so that pin can take it from there, or if something is coming from the pin in that latch, it will be saved for some time. So that type of circuit is available here. So how many? 4 IO ports are there. What are their name? P0, P1, P2 and P3. How are these ports? Both directional, because they are IO, input, output. We can configure them as input. So from P0, from these 8 pins, whatever is coming will be taken as input. So where we will configure, who will tell those pins are inputs or output? Again, in our program, we have to write in such a way that we will configure this pin. Look what language I am using, configuring the pin. So in the program, we will configure the pin as input or output depending on my requirement. Again, P1, port P1 of 8 pins and thus acting as 8 IO and internally 8 latches. Latch to latch the value as the name suggests. Latching, keeping the values. Okay. Similarly, P2 port and P3 ports are there of 8 bits. Okay. For example, in my what I need in my interface, To this port P0, I have to connect 8 LEDs. I have to blink those LEDs. Okay. Similarly, to port P1, I have to connect the keyboard. From keyboard, I have to take the value. So tell me, in this case, my P0 is acting like what? I or O? Input or output? I have to connect LEDs, 8 LEDs to them. So how it will be acting?
Output.
As the output port. And keyboard I am connecting, so P1 will act like input port, right? So that way I have to configure it in my program. Okay. Then other than that, for the serial communication, we have serial port. Okay. This serial port, it has reading or writing. Okay, reading or writing, 2 pins are there for the serial port. It has been used for USART, Universal Synchronous Asynchronous Transmitter Receiver. By that way of communication, you can use this TXD, RXD, and the serial port to have the serial communication. Okay, so that way the block diagram is there. This is not the architecture, but the block diagram trying to tell you the overview of our microcontroller. Okay, so I'll go to the next part. Now the block diagram will be clear to us from this. Okay, so shortly we'll go through the features of 8051 architecture. I'm expecting that you understood it, and this space is okay. So 8051, it is 8-bit processor or microcontroller. Its processor is of 8-bit. You can say like that. CPU can work, CPU is the central processing unit, can work on only 8-bit of data at a time, right? Data, if we are dealing with the data larger than 8-bit, what we have to do? We have to break it into 8-bit pieces so that CPU can process on it. Okay, my string of data, if it is large, I have to cut it one by one. I have to work on it and then to combine it somewhere so that I'll get the required output. That has to be done. 8-bit CPU with register. Look here, the important point is there. Which registers are there? In conjunction with CPU, there is accumulator, register B, and R0 to R7. These are some important register working in conjunction with CPU. CPU is doing the operation and its output, we can save it in what? Register bank. So register bank A, that is accumulator, and B, they are working in conjunction with CPU. Along with that, there is 16-bit program counter and data pointer. These are two more important registers, and they are of 16-bit. Which one? One is program counter, and the name, and the other one is data pointer. Okay. Along with that, we have 8-bit stack pointer. Generally, part of program has been taken on the stack. So 8-bit stack pointer is also there, pointing toward that stack. There is 8-bit stack pointer. Then internal ROM of 4 kilobyte. ROM amount indicate on chip program space. Obviously, you know it. If I need more program memory externally, I can connect to it. So these are some of the features. These are the 5 features. Let us see some more features. Then the internal RAM is 128 byte and some external RAM can be added. Okay. Again, 2 16-bit timer. We have seen 2 timers, T0, T1. They are of how many bits? 16-bit. One serial port is there. We have seen it. Then how many IO? 32 IO pin arranged as 4 8-bit ports. How many ports? 4 ports. And every port is of 8-bit. 6 interrupt sources. Then oscillator and clock circuit as we have seen in the block diagram. So in total, 40-pin dual inline package chip is available there for 8051. So this is what is clear from our block diagram. We will move to the architecture in detail. Can I expect you understood it?
Yes, ma'am.
Okay. Architecture is completely visible to you people?
Yes, ma'am.
Okay. So in the architecture, as we are talking about, this was our CPU. This was the part of CPU. Even I gave you one name, which is arithmetic and logic unit, called as ALU. And who is there in conjunction with this ALU is register A and register B. Is it right? This is the accumulator and this is B register. So whatever operation we have to do, the data on which we have to do the operation, that data has to come here in A and B, and then it will be fetched by ALU. Here the operation will happen and the result will be saved in A, and later on we can move it to the random access memory, or we can say we can move it to the register bank. How many register banks are there? Register bank 0, 1, 2, 3. This has to be specified. Where we are moving it, it has to be specified in our program. Okay. So are you getting? ALU, arithmetic, as well as in logic operation, whatever has been told by the program, by the instruction in the program will happen here. The output will come here in the accumulator. From the accumulator, according to our requirement, it will be stored in register bank, either 0, 1, 2, or 3. We have to do the selection of those register bank. How we can select the register bank, either to deal with 0 or 1 or 2 or 3, will be done using this PSW, which is the program status word. Okay. In this, 2 bits are assigned for selecting the register bank. If those 2 bits are 0, 0, which register bank we are selecting? Bank 0 we are selecting. For 0, 1, bank 1, and so on, we can select the bank. Okay. So this is program status word, and in that it is of 8-bit. This program status word is of 8-bit. In that, how many bits are there? 2-bit. For what? For selecting the register bank. Okay. So you got it. The data on which we have to do operation, that 8-bit, for example, ANDing has to be done here. ANDing on 8-bit and 8-bit. So first 8-bit will be in A. Second 8-bit will be in B. ANDing will be done. Result will be of how many bits? 8-bit. Okay. Maybe carry will be generated. So those 8-bit will be saved here. If something carry like thing is generated, where it is going? To the program status word. Again, for the carry, there is 1 bit which will be set high in the program status word. So that way we got the answer where? In A. That answer, depending on the requirement of the program, can be saved to some of the register, and we can go for the next instruction. So that is how the working is happening. Okay. Then the next thing is special function registers. In the RAM, RAM, what we have seen, how much RAM is there? 128 byte of RAM is there. And if you convert this 128, okay, into hex, it will be 7F. What will be the representation for 128? What I told you, it is a stack of 128 byte, means 0 to 127. And if you convert that 127 into hex, it will be how much? 7F. So that is a stack starting from 0, 0 going up to 7F. And from this 7F above, what it will be? 802FF. Are you getting? How much part is remaining? 802FF. That much part is remaining. So in that part, there is the special function register RAM. Are you getting? This special function register RAM, which has been shown here, or in general, the first RAM up to what? Up to 7F, and above 7F, it is used for special function register. We have the separate diagram. We'll check it there. So keep in mind, the RAM which we are using, it is going, this is RAM actually. This is RAM. It is starting from where? 0, 0, going up to what? 7F. Above 7F, what is the chance for the 8-bit? Our 8-bit will go max to FF. So that much part is used for special function register in the RAM. So some special function registers are there. And which are these special function registers? These are the special function register. Interrupt enable, IP, PCON, SBUF. We will go for them wherever required. These are all special function register. Keep in mind, they are playing very important role in programming. SFRs they are called as. Okay. And how to deal with the timer or interrupt or buffer or control register of the timer, that can be dealt by using this SFR. Okay, so the name SFR or special function register, and it is a part of RAM, and these are some special function registers. Now, I told you about A, B, ALU, PSW. In PSW, we'll go in detail with it. Then we talked about RAM. Now there is ROM. What is the ROM? Read-only memory is the program memory. And this program memory, we are burning our program while programming the microcontroller. At only once we are putting the program. Obviously, it is erasable programmable, but once it will be programmed and according to those instructions, our system will work. Then, supporting this program, there is DPTR, that is data pointer. It is 16-bit register and thus it has two parts. What? DPH and DPL. Higher 8-bit, lower 8-bit. It is the 16-bit register in total. We'll check its use. Okay, but look, it is connected with this PSW also. Then there is program counter. Okay, and this program counter is again the 16-bit. And look what is connected to it, 16-bit address bus. Our data bus is of 8-bit and our address bus is of how much? 16-bit. Because ROM is, what is the size of ROM? Yes, what is the size of ROM? 4K. 4K is the size of ROM. And for addressing 4K, you need how many bits? You need 16 bits for addressing 4K. Okay. And that's why for addressing the 4K, 4 kilobyte, you need 16-bit address bus. And that's why your program counter and DPTR, which are dealing with this program memory, they are of 16-bit. Try to understand this difference also. Our RAM is of 8-bit, data we are dealing in microcontroller is of 8-bit. Okay, whereas the program we are dealing, it is of 16-bit. So what do you think, how it is coming inside or how we are dealing with it? Obviously, in two parts, it has to be taken inside. For example, from some port, if I am taking the address, look here, port 2 and port 0. They are dealing with address A0 to A7, A8 to A15. Means MSB, 8 MSBs are taken from port 2 and 8 LSBs are taken from port 0, either given out or taken. So that way that we are dealing with 16-bit of address, either external or internal, it will be of 16-bit address bus. Okay, so just this much part I tried to explain you, and I'm trying to emphasize again and again that we are dealing with 8-bit of data, but dealing with 16-bit of address. Okay, means more program memory, right, compared to the data memory. Now, look here. After this, there are port 0, port 1, port 2, port 3. What they are doing? They are dealing with external world. All the IOs, either the signal taken in or the signal to be given outside. Ports are dealing with it. So there are these are the pin, then the port and the latch. I told you that a latch is required to be there so that something which you are giving out on the port stay for some time. It should not happen. You are given the signal and it is later on changing, directly changing. It should not happen. It has to be latched for some time so that my external circuit will sense it. Or if it is coming externally, it has to be get latched so that my internal circuit will sense it. Either or, going out or coming in, it has to be latched for some time. And that's why every port is having latch. So obviously, how many latches will be there here? Can you tell me in this latch? How many latches will be required? How many pins we are dealing with in the port? Each port is of how many pins? 8 pins. Is it right? Each port is of 8 pins and thus 8 latches. What do you understand by latch? How the latch is made up of? Please try find out the circuit of latch so that you will understand what we mean by latch. The flip-flop without clock is latch. Is it right? So that type of circuit. For each pin, one circuit. In that way, how many? 8. Here also 8 and 8 and 8. That way, latches will be available here. Okay. So we can take the input signal and we can deal with it accordingly. Okay. Or we can give the output to those ports. That way the external circuit is there. Now, exploring this external circuit, we'll talk about port 0. What has been written for port 0? IO, that is input or output. My port 0 works as input port or output port. The 8 pins of port 0 work as the input pin or as the output pin. Okay, other than that, it works as the address also. Which address? A0 to A7. For accessing the external program memory or data memory, the address A0 to A7 can be dealt with using these 8 pins. Other than that, I can use the port as D0 to D7 data pins also. From external memory, if I have to take the data or if I have to save the data on the external memory, I can configure it as D0 to D7. Try to understand. 3 things this port 0 is doing. One is IO, other one is as the address. Third one is as the data. And how to configure? Again, as I told you, our program will configure it what we want it to be. Do we want it to be IO? If I want it to be as the output, if it is connected to some LED, I want to blink those LED, then I'll configure it as O port, only O, output. Okay, whatever will be the program will go to that port and accordingly my LED will act. So I'll configure it as what? Only O. But if I want this port as the address bit, 8-bit address, then in program I will configure accordingly. And with help of port 0, I can connect to the external memory. Then, similarly, let it be external data memory I am configuring. And from that, I have to fetch the data as well as I have to write the data. I can configure my port 0 as data D0 to D7 pin for accessing that data. Okay, so these 3 important things it is doing. Now port 1. What it is? Just no other function, only IO. Port 1, it is supporting just input and output, no address or data. Whereas port 2, it is acting as IO as well as what? A8 to A15 means what? As the address, right? This is 8-bit of address and this is higher 8-bit of address it will deal with. Okay, so try to understand external memory, how much memory I can access externally. A0 to A7 and A8 to A15 means how many bit I got? 16 bits I got. And using 16 bit, how much memory I can access? 4K of memory externally I can access. Okay, so externally, if this as well as this is not sufficient, RAM and ROM, they are not sufficient. Externally, I can access that much of the memory. Now the port 3. Look, how is port 3? It is IO. Along with IO, it can act like the interrupts. external interrupts can come through this port. Counter, something I have to count, that signal can come from here. Serial data will come from here. Read bar, write bar will, for that serial data will come from this port 3. So port 3 is acting like IO, interrupt, counter, serial data, read write bar of the serial data. Okay, so we have completed this much part of the architecture. And in short, actually, I told you that these registers, they are part of RAM. And how many? One, two, three, four. Four banks are there. Every bank is having how many? 8 registers. 8-bit, 8 registers. Okay, so that way the register bank is there. And some part is byte as well as bit addressable. If I have to access a single bit, that also can be done in some part of the RAM. Even we talked about some special function register. Wherever required, we will deal with in detail this special function register. Okay. Then further, one more important part which is there in this architecture is system timing. Okay, with help of clock, we can set the system timing. Then system interrupt, timers, data buffer, memory control, all these things has to be dealt with, and they have been dealt using these pin. VCC ground, obviously it is required because we have to turn on the system. So VCC grounds are required. Enable bar, ALE, address latch enable, then PSEN, external 1, external 2. This is dealing with the clock and the reset. These are some pin to our microcontroller. So this is how the architecture is there. If you have any question on architecture, please let me know so that we'll clear it here and move to the next part. Is anyone any question? Because if it becomes two-way communication, then only I'll understand what you are getting. Else simply I'll go on giving you the thing. So please be clear about, because you have to understand number of microcontrollers. So you must be clear about everything.
You can unmute and speak also.
Yes.
So they can unmute also and speak. If anyone want to have any question, they can
Achha,
ask.
yes. I'm asking them so that what is clear to them will be known to me. Yes, participant.
Ma'am, generally in mobile phones we have ROM. In that ROM we can store the data, and also like we can also store the data, right? So in that case it will be writing to the ROM. But here in 8051 architecture, the ROM is unidirectional, but in mobile phones or like that we have bidirectional. Um,
Actually, when we say read-only memory, it is unidirectional only, not bidirectional. Because name is like that. Read-only memory. We can just read from it. We can't write to it. Okay. While programming by different method, by erasable, programmable, read-only memory means we can erase, right, and again write on it. Those are the method of writing the program in the ROM. But it is not both directional. When we are and some operation is happening, means I'm using that chip in some operation, then ROM is just, you can read from it, you can't make the change to it. By, as the name suggests, it's just read only. Whereas RAM is random access. There you can save the data, means give and take can happen in RAM.
Ma'am, in mobile phones,
What
like
name you are taking? I'm not getting that.
like in mobile phones, we use
Acha,
ROM
mobile
for
phone.
store. Yes, ma'am. We use ROM for storage and RAM for program memory. But here, uh,
No. Again, you are confusing. ROM is program memory. RAM is data memory.
okay, ma'am.
Okay.
Okay, ma'am.
ROM is program memory. So basically, whatever is the program, they are going to put it on the mobile phone, ROM of the mobile phone. Accordingly, it will act. Means one button is pressed, then screen will glow. That type of program, which is basically required, will be there on the ROM only. You can't change it. Okay. And some changes which have been given to you, so that through the RAM, they will get activated. Okay.
Okay,
Oh,
ma'am.
anyone? Any other thing? And that the thing which you are trying to ask, it is in system programmable thing, and they are available obviously there for the advanced processors. They are available there, but while dealing with 8051, we'll not talk about them, else it will create the confusion. Okay, so we'll move further. So we have seen that registers, how many bank? 4 banks of registers are there. And for what they are used? Registers are used to store information temporarily. It is in RAM. So it is the temporary storage. While the information could be a byte of data to be processed or an address pointing to data to be fetched. Okay, that is use of the register. What I can save there? I can save byte of the data. I have to process on some data, or I process the data, and that I am saving for temporary purpose, that I can store in the register. That is how I can use the register. Or address pointing to data. Even what I can save there is the address. And what is that address? Pointing towards some data. For the programming, it is required. So that is how the registers are used. The vast majority of 8051 registers, they are 8-bit, right? We have seen all the register bank A, B, they are of how many bits? 8-bit. There is only one data type, that is 8-bit, dealing with just 8-bit. Widely used register. Again and again, we are repeating those names because they are important. One is A, most important, working in conjunction with CPU. A means what? Accumulator. Okay. For all arithmetic and logic instructions, A has been used. Then what is the other register? B, R0, R1, R2 up to R7. And try to understand R0 to R7. These are repeating. How many times? How many banks are there? 4 banks are there. So R0 to R7 in bank 0, R0 to R7 in bank 1. That way it will go up to how many banks? 0, 1, 2, and 3. 4 banks are there. Okay. So 8 fours are 32 registers are there. And their names are same. Only banks are changing. R0 to R7. Right? And who is selecting which bank we are dealing with? Who is selecting it? What I told you? How to select that bank? Program status word. Who is there? Either we are dealing with bank 0 or bank 1 or bank 2. It has been shown by 2 bits in program status word, which is again working very near to your ALU. Okay. Then there is 16-bit data pointer and 16-bit program counter. It will come further. We'll talk about it in detail. Okay. The registers which I am talking about, how are those registers? This way the registers are there. D0, D1, D2 up to D7. How many bits it can accommodate? 8-bit it can accommodate. Ours is the register of 8-bit. Okay. And this is called as, on the right hand side, the bit is called as the least significant bit, whereas on the left hand side, it is called as most significant bit. Okay. So that way these bits are there. Now imagine the bits which are present here are 1, 0, 0, 0, 1, 0, 0, 1. What I'm trying to tell? 1, 0, 0, 0 and 1, 0, 0, 1. Okay. So as I told you, this will be represented in hex whenever we are writing down the program, whenever we are describing this register in the program, it will be in hex. So who will tell me? First 4-bit will be separately represented in hex and the next 4-bit will be separately represented. So for 1, 0, 0, 0, what is the hex representation? Hexadecimal representation. Hex means I am trying to tell hexadecimal representation. So for 1, 0, 0, 0, what will be the representation? 1, 0, 0, 0 means 8.
8.
8, right. And 1, 0, 0, 1 means
9.
9, right? And if I say 1, 0, 1, 0, then it will be
A.
A. Very good. So that way, hexadecimal representation will be there depending on what are the bits in your register. So these are the registers we are talking about. Now, this is the bank of register A, B, and these 8 register. Okay. So how is the stack? Every register is of 8-bit, 8-bit, and so on. So that way the stack will be there. Similarly, how is your DPTR? It is in total of 16 bits. So obviously 8-bit separate, 8-bit separate has to be there in case of DPTR. DPL and DPH, higher 8 bits, lower 8 bits. And one more register, which is of program counter, it is in total of 16 bit. Okay, now after understanding those register, we'll check how is the RAM, because RAM is most important part. ROM is simply the stack running from 0, 0, 0, 0, 4, 0 up to 4F of 4K, 4 kilobyte. Whereas RAM, it has separate part, and separate part is representing something separate. That's why RAM is most important. Okay. Later on, think of ROM. Try to draw it. Try to give the location to it. How? From 0, 0, 0, 0. How many bit? This location. It is representing how many bit? 8 bit. Okay. And then 0, 0, 0, 1. That way it will go on increasing up to what? F, 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 F means 4K. Try to convert it later on. So those many 8-bit stack is the ROM, but RAM. How is the RAM? Starting from 0, 0, going up to 0, 7. What it is accommodating from 0, 0 to 0, 7? 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, and 0, 7. 8 register. Of which bank? Register bank 0. And what is this width? This width is of 8-bit because we are dealing with 8-bit of data. Same way for register bank 1, 2, 3. In total, 4 register banks. What is the last address for register bank 3? It is 1F. After 1F, we are moving to 20. And what is there from 20 to 2F? It is bit addressable RAM, such type of RAM which is bit addressable. I don't have to deal with 8-bit of data. I have to change the single bit. That I can do here, bit addressable. Some program I need that type of thing. So bit addressable RAM is available here from 20 to 2F. And from 2F, what is the next thing? 30. 30 to 7F. What is there? Scratch pad RAM. Again, the scratch pad RAM is available here. Okay, and what I told you about this, what will be there up to FF? After 70, what is there? 80. From 80 up to FF, what is there? Who will tell me?
Special function.
Right, SFRs are there. Special function registers are available there. Okay, even this diagram is trying to tell us that 4 register bank and each bank has R0 to R7, and how they are selected by the program status word. These banks are selected. Which bit of program status word? 2 and 3 bit of program status word. Expecting you understood it. In case of any problem, please ask me. Okay. So after this RAM of 8051, we'll go to the program status word. We are talking so many time about the program status word, which was in conjunction with ALU. Whatever is happening in ALU, its reflection is going in program status word. Okay, even some part of the program status word is programmable also. Which part? These two bit RS0 and RS1. They are programmable. We can put, if I am putting 00, I am dealing with register bank 0. If I am putting 01, I am dealing with register bank, sorry, 00, I am dealing with register bank 0. 01, I am dealing with register bank 1. And 1 means which address in your RAM? 08 to 0F, that address in your RAM. Similarly, if here I am putting 10 programming and putting 10 in it, means I have to deal with, I have to work with register bank 2. Means in RAM, address 10H to 17H. H means hexadecimal, right? When I say 11 by programming, when I am putting 11 here, I am dealing with register bank 3 and this address I am dealing with. So what I told you, in PSW, we have 2 bits which are programmable. Now remaining bit we will talk about. This is carry flag. What is it? CY means carry flag. Which bit in program status word? MSB. That is 7th, as we used to call the first one as 0. That's why the last one is 7, means in total 8. So what is that carry bit? That carry or carry bit or carry flag, it will be set high. Who will tell me when it will be set high?
When it was 1.
Right. When in ALU, if the operation is giving, means it is working on 8-bit and 8-bit, and from the MSB, if both the MSB are 1 and 1, and we are doing the addition, 1 plus 1 is 1, 0. So 0 will come in your accumulator, MSB of accumulator, and that 1 will set the carry flag high. Right? So carry which is generated from the ALU will set this flag high. We will understand that carry is set there because in ALU we have chance of storing how many bits? Only 8 bit, right? That 9th carry, somewhere it has to be taken care of. So who is taking care of it? This carry bit is taking care of it. So that is carry flag. Other one is auxiliary carry flag. Okay. After 4 bits, first 4 bits, okay, in total 8 bit, starting from LSB, if the 4th bit, they are generating the carry, that is called as auxiliary carry and it is taken care here. Are you getting? From the first 4 bit, in that operation, if the carry is getting generated, that is called as auxiliary carry and that is taken care here. Then there is
Ma'am,
yes,
can you explain that again?
auxiliary carry.
Yes, ma'am.
Okay. Auxiliary carry is, for example, try to understand that in accumulator A, the value is 1, 0, 0, 0. You can write it on your pad also or on your notebook if you are doing it. So what I am saying in accumulator, MSB, starting from MSB, it is 1, 0, 0, 0. And then there is 1, 1, 0, 0. Okay. Whereas in B register, there is 1, 0, 0, 0. Again, same bit. I'm repeating 1, 1, 0, 0. So in hex, if I say there is 10, 11, A, B, C. 8C in accumulator as well as 8C in B register. Do you got it? What I'm trying to tell? What is there in accumulator? 8C. And what is there in register B? 8C is there in register B. What I want my ALU to add them. Can you give the answer of addition? Add these two things, 8C and 8C. What do you mean by 8? 1, 0, 0, 0. 1, 0, 0, 0. And what do you mean by C? 1, 1, 0, 0. So add it, please. I am adding at my level. Starting from LSB. LSB will give me 0. Then 0, 1 plus 1 is 1, 0. So 0, 1 carry. 1 plus 1 plus 1 is 1, 1. So 1 and 1 carry. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 1 is 1, 0. So 0 and 1 is carry. So what 8-bit I am getting is 0, 0, 0, 1 and 1, 0, 0, 0. Are you getting? Have you written it? Have you tried to add it? Can you tell me from the first 4-bit addition, is there the carry generated? There is LSB, then the next value, then the next, and then the next. Okay, that is the fourth one. In fourth one, it was 1 plus 1 plus 1. And it gave me one carry, which I have to carry further.
Yes,
That
ma'am.
is auxiliary carry, which is happening. And even,
Okay.
so carry is also generated in this operation as well as auxiliary carry is generated. Is it right?
Yes, ma'am.
2 flag will be set high, carry and auxiliary carry. 2 flag will be set high in this case. That is auxiliary carry. Now, the F0, it is available to user for general purpose. This bit has been kept for user. Then RS1 and RS0, we can use them for bank selection. And that bank selection, I told you it has been given down here. This is OV. OV means overflow. If our register is overflowing, then in that case, this flag will be set high. One more, this bit is again kept user defined bit. And this is the parity flag. P means what? Parity flag. Set, reset, odd, even parity. For showing the parity, we'll check that parity operation. So this flag has been used here. So what we have to keep in mind is maximum flags are set using PSW. We have to keep check on PSW, and on basis of PSW, we have to work in the program, right? Because it is telling that is the carry generated, is auxiliary carry generated, is the parity there, is the overflow there, which bank we are using, everything has been shown by PSW. So it is one of the most important register we have to take care of while programming 8051. Is it right? I would like you people later on even to check carry and auxiliary carry if you have any doubt about it. Any doubt? Anything remaining? Okay, I'll go further. So we have described it. I'll not read it. Program status word. In detail, we have checked the program status word. Okay. Even I would like you people to program it. Try programming 8051, and whenever you are writing program for 8051, go and check for this register. It is possible for us to read those registers. Okay. And what is happening there? That will give you very good insight how the flags are getting generated. Okay. And how the registers has to be used. Okay. I will go further.
Madam,
Yes.
in this course, what syllabus we are going to cover?
In this course, from my side, I am covering 8051. Then the next architecture is PIC, which I am covering. 8051 is timer, counter, whatever are required for programming that we are covering. Similar thing we are doing in PIC microcontroller. Then we are going to move to ARM. Okay. Even ESP32 is there. So
ARM which controller, madam?
ARM LPC 2148 we will deal with, and then if required, Cortex.
Okay.
Hmm?
Okay. Thank you.
Is it possible for me to clarify the things? Are you understanding the architectures?
Yes, ma'am.
Okay. Now, look here, the SFRs. Few SFRs, I describe its name. Few, I kept it as it is. So these are the SFR, particularly putting those SFRs in front of you. One more thing I would like to tell you people is assembly level language has its own what you can say instructions for 8051, and the higher level language is C. Generally we are using C and not going for assembly level language. So assembly level language is the language working in conjunction with ALU, whereas for our better things, or for us to make the thing easy, we are working in C. So if you get the time, if you want in detail this 8051, once just try to go through that assembly level language also. Anyway, we'll come to this SFR. So look, these are the SFR A or ACC. A register, or it is called as what? Accumulator. And what is the address in hexadecimal? E0 is the address. In the RAM, where it is available? Obviously, everything is in RAM. When you are going for input output, means you can store something and you can access it. It has to be both way. So where it is available, what I told you, when both way operation is required, it has to be in RAM. So at what location of RAM it is available? E0 location of RAM, right? Register B, where it is available? This is available at location F0. A and B, they are working very near to our ALU for putting 8-bit data, 8-bit data. Its result, where it will come? To the accumulator it will come. So which address it will be there? E0 it will be there. Is it clear? Then there is data pointer higher order register. As we know, data pointer is of 16-bit. So higher 8-bit, they are available at 83. And data pointer lower 8 bits, they are available at address 82 of RAM. Then IE, which is interrupt enable register. As we have seen, many interrupts are there. In total, how many sources? 6 sources of interrupts are there. Okay. So those interrupts, do we have to consider them while programming, or we don't want them, either to mask them, we don't want them. So that way, or do we want one or two and others has to be kept aside? That we can write here in this register. What that register is called as IE, that is interrupt and enable. Which interrupt to be enabled and which one not to be enabled, that we can decide from here, and available at the address A8. Obviously, we don't have to remember this address, but we must know how these registers are working. Okay, so that we can incorporate them in our program. That is most important thing for us. Then there is interrupt priority register to set the priority of interrupt. Whatever interrupt I am enabling, in which one is having highest priority, which one is on the second priority, and so on. Right? For example, where to put the example? In some system, for example, in a washing machine, my water tap, if it is not running, that is let it be the highest priority. At the second priority, the door of washing machine is closed or not, that is the second priority. So these are interrupt coming on the program. So in washing machine, though I am turning on the main, setting the program and turning on the program, what is happening? My program will check for interrupt. So which two interrupt I am talking about? One is the tap running? Is there water in the tap? As well as door of the machine is closed or not. So what I told you, door is closed or not is the second priority. What is the first priority? Water in the tap is there or not. So that priority you can set using this register IP. and enabling those to interrupt where it is happening. It is happening in interrupt enable register. Okay. Now, the next thing is port. Though the ports are there, 8-bit ports are there. Okay. But either we are using them as the input port or output port. Programming them is happening here. P0, those 8 bits, where those 8 bits are available at the address 80 of RAM, port 1 at 90, A0, and so on. So these are the address of your port. Then there is power control register PCON. Okay. Then there is program status word. We have seen it and it is available at D0. SCON, which is serial port control register. There is one serial port, right? For controlling it, there is the register SCON. Serial port data buffer. For that serial communication, buffering the data, keeping the data. What do you understand by buffering? Keeping the data for some time. It is happening in S buffer. Okay. There is stack pointer pointing toward the stack, which instruction is getting executed. Now, what is the next instruction? That is pointed by stack pointer. There are the registers called as TMOD, which are either used for timer or for counter. If it is internally used, it is for timer. If we have to externally count some event, it is for counter. Similarly, TCON, these are control registers. What is above one? It is mode, selecting the mode of timer, and this is the control register. Okay. Other than that, as we have seen, we have timer 0 and timer 1. Each timer is of 16 bits. So the lower 8 bit, upper 8 bit, lower 8 bit, upper 8 bit. So that way we have SFR. All these are SFR. I want you people to go through the short form as well as long form of this SFRs. Take 1 minute, go through it once. Obviously, not all the SFRs, but few of them we have to further analyze. Is any doubt about these SFRs? Do you understand the address, what I'm trying to tell? These address are of what? RAM. The address of RAM is there. Okay, so I'll go to the next part. This is called as the programming. 1 minute. This is the all the registers, what we talked about with its address as well as its how many bit it can save. That is given here. So once very shortly, whatever we have done till now, from here we'll try to collect it. If you people just see the thing, it will be easy for us. So look here, internal ROM is going from 000 up to FFF, covering 4 kilobyte of ROM. It is the internal ROM, it is of 4 kilobyte, and it's just this type of stack. And its width is 8 bit. That is only the description of the ROM. Okay. Here, we are burning our program. We are configuring our program, writing our program here. Okay. Then after that, this is RAM. And we have seen the RAM in detail. Its lower address is starting from where? 00. That way, how many registers? 7 registers. From 00 up to 07 means 8 registers in each bank. So this is bank 0, bank 1, again 8 register, again 8, and again 8. So 32 register and address is ending at 1F. After that, from 20 bit addressable memory, from 30 general purpose area, and above that we have SFR. Okay, those SFRs with their address are given here. Just once go through them. A register accumulator, it is of 8 bit, its address is EO. B again of 8 bit, its address is FO. IP register, it is of 8 bit, its address is B8, and so on. Okay, so that way the things are there. Out of it, we'll just identify this is our program status word. This is our program counter. It is of 16 bit. This is data pointer. Again, it is of 16 bit, 8 bit, DPH, 8 bit, DPL. These are 4 ports, all of 8 bit. Okay, and this is some direct byte address indicate bit addressable. Okay, some bit addressable memory has been shown here. That way, with the address, everything has been given here. Okay, so it was bit repetition, whatever we have done. Again, the same description is available. That's why I'm going out. And here, type of, what memory is externally we can interface with 8051 that I am putting in front of you. What you can tell from here, just check the diagram once so that I'll come to know what you understood. There is 8051 chip. It's internal RAM. How much is this internal RAM? Just tell me.
128.
128 byte. And this internal ROM, which is electrically erasable, programmable, read-only memory, is 4 kilobyte, right? And then externally, how much data memory you can connect? From 0000 to FFFF. If you remember, 2 ports are there for address A0 to A7 and A8 to A15, 16 bit of address. And these are the 16 bit, is it right? FFFF means how many bits? 16 bit. That much data memory you can access externally. Similarly, that much code memory or program memory, that is 64 kilobyte of data memory externally can be connected to 8051, and similarly 64 kilobyte of read-only memory, that is program memory, can also be connected. That much extension can be made. We don't have to limit to 128 byte and 4 kilobyte. That much can be externally connected. Okay, and for fetching the data, if I have to fetch the data on the port 0, the chance is there. And for the address, port 0 and port 2 for giving the addresses are there. But try to understand the same bus we are using for address as well as for the data. So whenever it has to be separated out, either I am going for address or I am going for data, there is one pin called as address latch enable. What it is doing? From the address, it is allowing us to shift to what? To the data. Once address is given, look, for example, from this data memory at some location, data is saved. I have to take that data. So at first, what I have to do? I have to tell this memory that this is the address. Let it be that address is FFF1. That is the address. Okay. So at first, what I have to do? Using 2 ports, I have to send that address. Once the address is sent, it will give me the data. And that 8 bit of data, my data is just of 8 bit. Okay. That I have to bring here inside. Right. So who is doing that separation? ALE. What pin I am trying to tell you is address latch enable is helping us to separate out between these two. Okay. Okay. So external code memory of 64K and external RAM of 64K. That much is what we can connect externally. Okay. Anyway, I'll not go in detail of this. It is the same thing. That's why I'm not telling again. This is what trying to tell you that Atmega 89C51 and from Dallas Semiconductor, if 8051 is there, what is the difference in the ROM? What they are trying to tell is 4K of RAM is available there in Atmel, okay, and 8K is there in 52. 89C51 it has 4K, 89C52 has 8K, whereas in case of semiconductor from Dallas, it has 32K. Anyway, it is not making much sense. I'll come out of it. We have seen the RAM, so I'll come out of it. You got the register banks also, so that is also done. Okay, now I'll move to do I take the next point or we have to stop here? It is more than sufficient for today. And even there is one question here. You are from EC and you are interested in VLSI job opportunity internship training institute. Okay. And you want from me that how to crack for the internship or to get the job in VLSI industry. Okay. So actually, going for the VLSI industry, they need obviously the VLSI engineer, and you have to be clear about the concepts of digital. Along with digital, your analog circuits, where you are dealing with the diode, transistor, and MOSFET, because nowadays the chip, they are made up of what? MOSFETs. Okay, so that also has to be clear. Along with that, the network theory, wherever you are dealing with RLC, look, whenever the components and those wirings are going on the chip, they are making the circuits of R, L, and C, resistor, inductor, and capacitor. So dealing with that type of the circuit, obviously it is happening in second and third year of ECE, generally electronics and telecommunication engineering or electronics and communication. That's happening in first, second, third year of those engineering. So be good in those concepts. That is very much important. In parallel, from say third year onwards, generally the microcontroller, then embedded systems, they are coming. Because nowadays what is getting developed is the chips of microcontroller or maybe some processors they are developing. So the what new thing we can add to that chip, that is also required. That's why embedded is also playing very important role. Embedded microcontroller, they are also playing very important role for VLSI jobs. So be clear about them. These subjects, they are required. Okay. Then if you are, maybe VLSI is one of the subject to you, it might be in final year graduation. Okay. So there you can clear more thing. Actually, VLSI industry, they are not asking you much that do you know system Verilog, do you know what UVM? They are training later on. But at first they want all the basics from you people. So be clear about it. Okay, that is what I can suggest. Any other question?
Yeah, class is over, ma'am. Class is over.
Shall I stop here?
Yeah, we can stop here.